Whether you are building simple CRUD applications or data processing pipelines, message brokers, distributed database, in one way or another you are faced with the challenges distributed computing brings. The luckier one among us live only on the happy path and face none of the problems that distributed computing carries with itself. However, the other group of us is usually encountering a long-running, very difficult to identify and tackle issues on a day-by-day basis. Some years ago, during the 90s, Peter Barch and James Gosling came up with a list of mistakes made during design and implementation of distributed systems. This list is commonly known as 8 fallacies of distributed computing. While it can be challenged that these fallacies, the impact of some of these fallacies has changed over the years, it is absolutely true that they carry consequences that can very easily point them out as the root causes of some of the commonly known problems in distributed environments, such as failure detection and recovery, split brain issues, scalability problems, problems with performance, various security breaches, and many other exotic and less exotic issues that you tackle on a day-by-day basis. As functional programmers and enthusiasts, you're free to ask, where are my monads? Because you can make a claim, and I believe most of us agree here, that a landscape for distributed computing in Scala ecosystem is ignoring more or less all of the benefits that we have in a single node computing, like referential transparency, equational reasoning, type and resource safety. Once we reach the world of distributed computing, most of these are gone. That being said, and having in mind the previous concerns, all the practitioners in the domain spend most of their work hours like this. Today we want to present you an alternative. Over the past couple of months, we were building a library called ZeoKeeper, which is a purely functional, type-safe library for building distributed systems. While designing it, we come up with a couple of goals that we consider to be the most important for one such library. All of the primitives exposed by it should be composable and replaceable. This effectively means that users of the library should not be forced to cope with the decision made on the lower level before them and be able to replace, for example, the consensus algorithm or to replace the membership protocol in use depending on their use case. We should be failure-friendly and detect all the failures as early as possible and provide reasonable defaults for handling them, as well as the option for users to specify more fine-grained, customized recovery strategies. Of course, all the primitives should embrace strong types and should guarantee that no resource will be leaked. And last but not least, take this with a grain of salt, we should have security in mind. For the first iteration of our work on ZeoKeeper, we decided to narrow the scope of security concerns to providing encryption on the level of message transport, but also having in mind that not all of the potential use cases have a need for such feature, we decided to make security an opt-in feature. So you can or cannot choose to encrypt your messages under the hood. ZeoKeeper is built predominantly on top of Zeo, utilizing its concurrency capabilities, strong types, as well as resource safety guarantees. But beside the core library, we also use ZeoNeo to utilize the transport capabilities that carries with it and byte buffer handling strategies, as well as ZeoLogging to provide us with basic instrumentation via logs. And last but not least, we want to make our interfaces as ergonomic as possible, as well as to scrape boilerplate from our internals by using Zeo macros, which you will hear about more tomorrow and Maxim talks. Roughly speaking, the library is comprised of 3 layers: transport, membership, and consensus. Inside the transport layer, we are concerned about providing a way to transport messages from node A to the rest of the cluster. Currently, we support both unicast and broadcast messaging, and we guarantee both reliable and best effort manner of transport. At this layer, we are also concerned by the way how messages are serialized, and for the first version, at least until Zio codec is prototyped or done, we opted in to use micropickle as a serialization foundation. Also, as I mentioned previously, message encryption will be an opt-in feature at the transport layer. On membership layer, we take care of building and maintaining dynamically sized clusters. This layer provides the user customizable discovery strategies, as well as multiple membership protocol implementations. At the point of this talk, we support two membership protocols, SWIM and HyperView, and two discovery strategies. One is basically a static discovery strategies where we provided a hard-coded list of seed nodes that you use to connect to, and the other one is built on top of Kubernetes DNS capabilities. The most controversial of all layers comes up the last, which is a consensus layer. Here, we need to solve the problem of data consistency and at one point of providing a viable leader election strategy. This layer is, of course, also completely open for discussion and designing at this point. And the most concern we have about the choices of which primitives we are going to expose. We are discussing whether to go in to some more well-known algorithms like Paxos and Raft, or to go toward the lenient path with CRDTs. But we are open to suggestion, and I think we would benefit from the input of a broader community at this point. I would like to give Shem a chance to demonstrate how our membership and gossip layer work.
Okay, guys. So what we're gonna do is I'm going to try to do almost the live demo. Let me see. There you go. So, Dejan mentioned about our layers. So I'm going to start with transport layer. And for purpose of today's presentation, I'm going to build like a very simple TCP client-server application. I'm going to start to show you what we mean by those layers. So the layers are, if you're familiar with Zio already, this is the services, or some people say the modules. So it looks like pretty much the same as console or cloud. And our idea is that it should be like as easy as sending a message to the other machine as like printing the something to the console, right? So the interface consists of two methods. One is connect, which is taking the address, and the other one is bind, which is taking the address, and the connection handler, which is the function that pretty much defines what you're going to do with the connection when it's going to be accepted. Okay, so this is our TCP server. So nothing special here. We have Zio app. If you are familiar with CATS, this is very similar to the IO app. So run is our main that we return our effect, and the program is just like defining the logic in this case. So what we have here, we taking the local address, we creating the public address with the socket address. Those two things comes from Zio Neo. Then we creating the logger, we creating the handler, right? So the handler is this channel is pretty much like a poorly named connection, and we're gonna implement like an echo server. So it's like we're taking data from the channel. So we're gonna read some bytes. Then we're gonna print it on the console and then send it back, right? as you notice here, this guy is a chunk, and the chunk is just like a wrapper for arrays. So we are not, like Dejan mentioned about the serialization, we are not providing serialization on the user layer. It's like just the serialization that we choose to be implemented on the backend for communication between the nodes. Of course, we're catching all the exceptions and we log them appropriately. And then, since the interface says like the bind is returning manage, because we care truly about the resource allocation, we're providing the public address, and then the header, and we say, okay, we're gonna use this forever. So that is the logic, nothing really advanced here. But to make it work, we put in some dependencies. So of course we are heavily use the environment from Zio, and for all of the building blocks we provide as well the enrich M from Zio macros. So in this case, what we're going to do, we're going to create the TCP transport with 10-second connection timeout and 10-second request timeout. This guy depends on the logging, so we create the logging service as well. We're going to wire those two things together and run the program. Okay, so that looks if that actually works. And now that was a little bit too brave to run the live, but we'll see. Okay, so we have the server up and running. So let's try to connect this. Okay, first of all, I'm gonna try to connect with Netcat to see if this is really operating. So yeah, connection is accepted. The protocol for the transport is very simple. So we first we're sending the integer with the number of the bytes that we're gonna read. So let's say we're gonna say 6, and then we're gonna say full bar. Oh, alright, so wow, yes. Okay, let's look into the implementation on the client in this with the transport. So the dependencies are pretty much the same, right? So no different in here. The only different is we're connecting to the address, then using manage, we're taking the connection, we taking the current time and just like sending like 100 messages. Again, very simple. But let's see if that works. Yeah, I'm not gonna check if there's 100 over there, but it seems to work. At the end, the connection got terminated, so everything is success, I would say. So as you see, very simple, like a little bit low level, but it might be very handy when you're trying to build something that is on top of the TCP. In the future, they mentioned that we support UDP. We are done yet, but implementation of this will be very simple, and we would probably just changing this with UDP transport, and then it should the entire logic should be exactly the same. You might also think, Adam mentioned before, we can easily implement in memory. The transport that will be very easy to use in the test, so then more complex, more consistent can be tested locally without using the remote. Okay, let's look into the something different. So this one is about the membership that. So the membership is, again, very simple interface that gives you the ability to access what is your local host, what are the members on, in the cluster. You can subscribe to the events in the cluster, like who is joining, who is leaving, who is becoming unreachable, things like that. We can send a message to the particular node. We have a broadcast that is controversial a bit and probably gonna be revisited in the future. And we have a receive that pretty much give you the stream of all of the message, and you can do whatever you want with them. Okay, let's look how this is gonna be useful. So this is a little bit different from the fact that we are using the manage app. So manage app is like it's almost like a ZO app, but we're returning the zmanage. So let's start with the program again. So we're taking the local member, and we broke when starting the node, we just broadcast to all of the guys, my local member, only to show you that local member is there and sending something. And then we're gonna take the receive. Okay, this is the stream. We just for every message that is going to reach our node, we're gonna print the log statement and then send to the sender, and sender is always part of the message. Then we're gonna sleep, and then we're gonna do this again. Okay, what about the dependencies? So dependencies are, as you might expect, there is a new dependency which is membership implementation. Right now we have a swim, which is like a simple weak evidence. I don't remember the name, to be honest. But it's the cool thing is about the simplicity. So the protocol is pretty much sending to the random node ping, and then expecting ACK. And if this ACK is not returned, it's trying to ping through the other nodes. And if that's not successful, then it's considered the node to be died. Of course, the paper about swim is also talking about more robust strategies, trying to put this in the suspect mode that supposed to decrease number of false positive in the failure detection, but we don't have that yet. It is work in progress. Okay, so we have a membership, and the membership, as you see, is depending on logging and transport, which you have seen already, and it's not different. The new guy here is discovery, right? So in our very simple example, here we just create 3 local host address on the different ports, and this is the strategy that you might have seen in Anka cluster, that you provide the seed of the node, because when you start in cluster, you need to connect to something, right? And this connection is crucial at the beginning to get information about the cluster, and then form the cluster properly and connect with all the nodes. And this one is providing the static list. There is another one that you might just replace one with the Kubernetes, which will be get the address of the Kubernetes service, and then just use the Kubernetes discovery that will just ask the DNS for all the nodes and trying to connect with a couple of them from top of the list. If it's failed, it's trying to keep going. Okay, as mentioned, logging and transport is exactly the same. And let's try to run it. I'm gonna start 3 nodes and see. Hopefully they are not failing. Let's see if they're able to connect to each other. So at the beginning, as you see, it's trying to connect with all of the seats that I mentioned. Of course, they are down, so this guy become a seed because I choose the port from the list. And it's starting accepting connection and it's starting the swim protocol. Right now there is no one to talk to, so it's pretty much fine, but not doing anything. Okay, and now they start talking to each other. As you see, those pink messages are going back and forth with ACK messages, right? All those messages are passing around the state of the cluster, and whenever I'm receiving the message, it's trying to converge my state with the other state that is coming from the remote. Let's try to add one more. Okay, and they are talking to each other. So now, the final, because this is the last thing, so if it's failed, it's fine. I'm going to kill one of them and see what happened. So the one of them is already, yeah, both of them already know that, okay, the message sent was failing, but that is not enough to make, yeah. So this guy is already realized and removed the node from the cluster, and the other one as well. And the cluster is keep going. Okay, so my takeaway from this presentation will be the distribution system implementation will be, I guess, always hard, right? Implementing those algorithms is difficult and painful in many ways, but with the Zookeeper, we will try to make it a little bit easier, and composability and resource safety is like a big thing on that. I'm handing over to my friend to tell you about the future.
All right. I'd like to wrap up the talk with a small glimpse to the close future for Zookeeper. Our goals for 2020, let's say, are first to come up with the first public release. We have a membership and transport protocol layers that Przemak demonstrated that requires a bit more polishing, and we will try to do that as soon as possible because A, we want to get some feedback from a broader group of people, and B, we want to unlock the work on an emerging library in Zio ecosystem called Zio Analytics that would depend on it. Once we had that, we would like to improve our instrumentation, first and foremost by integrating with Open Tracing and Prometheus, for which we already have existing libraries inside the ecosystem, and hopefully eventually with ZMX, as soon as possible that comes. And the big goal for next year, I would say, is to come up with a proper implementation of leader election. This would be something that will require, I guess, most of our time and most of the, hopefully, contributor/community effort. And finally, by the end of the next year, I hope to come up with a goal for which we started this library, hence its name, to come up with a distributed key value storage for storing metadata. Last but not least, I want to thank you for attending our talk, and check out the existing sources as well as the example on our GitHub repo, and join our Discord if you want to reach us.